So, as I said, I'm Leslie Hart from NOAA CIO office. I'm in the HPC group there. We sort of herd cats, more or less oversee what the field offices do in terms of HPC. Recently, Congress appropriated some funding for us to do some software engineering for what was termed in the language fine-grained HPC architectures. And the idea is to take applications and prep them for these architectures. And the question might be, what is fine-grained? And so the way we phrase it in a recent procurement document is a processing unit that supports more than 60 concurrent threads in hardware, meaning a GPU or a large core count device, mic. Of course, the real problem here, or maybe a good thing for us, is that the traditional architectures, as you're starting to push forward into the beyond Broadwell, you're starting to see large core counts, and arguably with hyper-threading and such, you can get up to around 60 threads on what we might consider to be a traditional architecture. So it's a moving target. And it's a moving target in a lot of different ways. So we call them novel architectures, basically most anything that other than Intel x86, I guess, or P8, P9, that kind of thing. So that's what our main goal is moving towards these less easy to program architectures. Actually, I should go into this mode. Sorry. Okay, now why is it doing that? Oh, it's doing the right thing up there. So really the overarching goals of our project are to really prepare codes for a future production system. And by production system, we mean either the operational systems in the weather service that run the codes that provide your day-to-day forecasts that you get out of our weather service forecast offices that provide warnings and those kinds of things. But also production in terms of many of our researchers are running their day-to-day codes, especially in the climate world, where they have a fixed code that they run hundreds of different scenarios against, and then use that to evaluate future climate changes. And so that's really how do we get the codes ready for those sort of things, and part of that includes the software part, but also keeping aware of what's going on architecturally. Another thing that's really important is the codes are not static, and I think as Rich Loft talked earlier, is extracting a piece of code from the mainline repository, optimizing, and then putting it back in. It's really important that when we put it back in, that the subject matter experts, the meteorologists, the climate scientists, etc., can still modify the code. We don't want something coming back to them that's so unrecognizable that it either becomes a static code or they feel they have to start over again. And these people worked really hard to get their PhDs in climate science or meteorology or oceanography or whatever, and they're not really wanting to do software engineering themselves. And part of this is monitoring or participating when appropriate, evolving standards like OpenACC, OpenMP, and the like. Codes, as they're transitioning, they still need to be viable for the current traditional architectures, because the codes, again, are dynamic. The modelers are still working on the codes as we're taking and working on them as well. So if we fork off a static piece of code, by the time we're done with it, if we're modifying it into, say, a different language or just in some way that's inappropriate for the existing architectures, when we come back, it's going to be so out of date it's not going to be relevant again. So it's important that we try to work with as much as possible with a single source tree. And the other side of that is that we've discovered as we do this that we get very significant gains in some cases on the traditional architectures as well. If you manage memory more, manage cache lines better, all those kinds of things, they're good for the x86, they're good for the P series or whatever. So it's important that we keep the code viable for the traditional architecture. It also lets us make really fair comparisons. I'm sure everyone here has seen the 40x, 100x performance gains of code A over something on a GPU or a mic, and it's always an old architecture, an old code that's never been optimized versus something that's you've locked a benchmark in a room for a week until he comes out with something really fast. So it really gives us more fair comparisons when you take those optimizations back to the original architectures as well. And of course, we need to build, either through contracts or through collaborations with universities, expertise within NOAA so that it's not a one-time thing. As these codes do continue to develop, that we still have the expertise around to continue to help us to monitor the changes in codes, monitor changes in architectures, and all those kinds of things. There's a leadership team. I'm out of the CIO's office, and then our three major HPC user sites are GFDL in Princeton, and here in Colorado, up in Boulder, Esrel GSD, and NCEP, which is the operational arm of NOAA, which is in the DC area. Actually, the people are in College Park, and the computers are in Virginia and Florida. So first thing we did is we stepped back and looked at the suite of models, which is fairly significant, and tried to set some priorities. And of course, WRF is a pretty universal model. It appears in a couple different ways in our operational suite as well as a lot of our research work. Primarily the ARW version of WRF, but also the NMM version as well. Earlier, the NGGPS project was mentioned, which is trying to select the next generation global model. And the two finalists for that are MPAS, which comes out of NCAR and ORNL, LANL, I believe, and FV3, which comes out of GFDL. They're both they're non-spectral models, so they don't have pole problems and those kinds of things, and scale a bit better, are easier to scale. And the GFDL climate model, which includes MOM and FV3 and a number of other codes as a Earth system model, and NMMB, which is a regional forecast model out of NCEP. So those are the models we're really focusing on initially. The other parts of this are, of course, doing programming research. I don't think there's no really settled art yet for programming these. We're getting there, but certainly algorithm development and deciding on a programming approach is something that is evolving for us and we're working towards. And of course, monitoring, participating in OpenACC, OpenMP, and watching how the LLVM compiler backend infrastructure evolves and how it injects itself into the various compiler suites that are available to us. The number of challenges. There is a lack of standards across divergent architectures. OpenMP seems to be, more aligned with the Intel PHY architectures and the like. And OpenACC seems to be more for attached processors. There is some convergence appearing there, but it's not there and probably won't be there for a while. So another challenge is we have a large quantity of legacy codes. The climate models by themselves are over 1 million lines, and then there's the WRF and aside from that small list of codes we have, there's another couple dozen codes out there that some are single processor or some are smaller scale models. Access to development platforms, certainly we've done pretty well there, getting access through TAC, through Oak Ridge, through NASA. But it becomes, you're constantly looking around for who's got the latest architecture. And certainly the small scale tests, when you go to an Oak Ridge, they want you to have a petascale code. Well, we're just starting to parallelize the code, or we're just starting to optimize the code for a GPU in the case of Titan. And you're not really ready for the petascale yet. And so that in-between stage, really, we're trying to set up what we refer to as a petting zoo, a small number of boards of different types, so that we can do some of the initial testing before we're ready to go out to, one of these large petascale and eventually exascale sites. Certainly, an interesting one that's more of a political problem for me, myself, is uncertainty performance gains. At the last procurement, we ran off Haswell against other architectures, and they really couldn't compete at that point. Haswell was a big jump forward. The fine-grained architectures hadn't made their jump yet, so when you go to senior management and you say, hey, this really isn't the right solution right now, you get a bit of a funny look from them sometimes, and you have to deal with that. And so, even going forward, it's not entirely clear that these fine-grained architectures are always going to be the solution, or that they're going to save us all from ourselves. And then, of course, I think a lot of people face this, is finding the appropriate and qualified staff to do this, especially if you look into a computer science department. The new graduates don't want to program Fortran with MPI and OpenMP. They want to go off and write the next great app for a cell phone, or do web e-commerce or something like that. So it's harder to find people. We're finding a lot more success in looking in engineering departments and science departments and things like that. But even there, it requires some training, or you don't really find somebody who can really hit the ground running unless they're already employed and already at this meeting. But technically, I think a question we have to sit down and ask ourselves, and we've kind of rumbled about it, but we really haven't formally asked ourselves this question, is Fortran MPI still the right choice? Well, we've got several million lines of code in Fortran and MPI, so we're kind of stuck with it for a while. But as we go forward, is there a complete re-engineering effort we're going to have to undertake at some point? Or is Fortran 2020 or 2030 going to be so different that it's going to be the right choice again anyway? Crystal ball's not really clear on that one, but I think it's a question that we haven't actually revisited, at least within NOAA, as seriously as we ought to. And a couple talks ago, again, the multiple layers of parallelism came up, and I think it's something we're all facing. There's task parallelism, then you've got thread parallelism, and then you've got these long vectors on both the Intel Phi and the GPUs. And so managing those multiple layers of parallelism and how to arrange your loops and your data structures and everything so that you can exercise all three levels of parallelism and get the performance you need. PCI bus kills us. I think everybody knows that. And so moving data back and forth between the GPU and the CPU and back again is clearly not the way to go, at least for the kind of codes we have. And so the memory footprint of the fine-grained device is just barely getting big enough where we can keep our code in the GPU or the Phi or whatever, and start really only ship data off to the CPU or over the NVLink or whatever for MPI communications is certainly leading to a lot better performance for us. So, making things fit, being more frugal with temporary variables and things like that is extremely important. And I think Rich Loft talked about this one as well. Atmospheric codes tend to stream through data. They don't take U and V and operate 15 different times on it before you move on to the next thing. You operate on the winds, then you operate on the temperatures, then you operate on the humidity, then you come back to the winds again. Well, it's all out of cache by now, so certainly I really appreciated his point about peak flops doesn't matter. It's really about memory bandwidth and about how our codes can take advantage of the memory bandwidth. So where are we going? This is a pretty new project. We're really talking about, and we've been doing some of this stuff for years, because while the funding is new, these efforts have really been going on for a while. Developing or cultivating relationships with vendors such as Intel, NVIDIA, Cray, our incumbent at the computing facility in Virginia. So developing these relationships so that we have more access to their compiler writers, their technical support staff, not just the sales guys. Working with internal tools such as source-to-source translators. We've been doing a lot of that for probably a dozen years of trying to implement a single source and then translating it out into something appropriate for whatever architecture we're looking at. That's been pretty successful. We'd really like to get out of the compiler business, though, so working with vendors to ensure directive-based approaches are feasible. And some of that has tangled these two together. The guy who works on the source-to-source translators will mock up an OpenMP command or an OpenACC directive and demonstrate the performance. Then he'll go back to your favorite compiler vendor and say, gee, mine's twice as fast as yours, and I'm only one guy. What's wrong? And so that turns out to be pretty effective. We'd really like to see the compiler vendors be the more preferred approach for us, so we can free our people to just work on applications. And again, the petting zoo concept, developing small test environment locally so we can do the single to 4 node sort of test locally, and then have an idea when we go to these big machines that DOE, NSF, NASA tend to have. And that also includes bringing in the hardware, compilers, and tools that we need to work on the codes as well. Again, the funding is distributed amongst our big 3 HPC user sites. And when Congress passes a budget pretty late and then you start moving it through the whole government system, we're really just starting the hiring process at most of the institutions right now. And they're through contracts and through collaborations with universities and the like, and that's ongoing. We're starting to bring in test systems. We're really continuing work on models. The model work has been going on for a few years now. And as, for instance, when we settle on whichever global model we want, we'll start working more collaboratively with the owner of that model to make sure it's targeted for the kind of architectures we're looking at. And we're running off OpenACC and OpenMP versus our own internal source-to-source translation, and secretly hoping that the open standards will win so that we can, again, get out of the compiler business. There is some synergy within NOAA. The next generation global prediction system, NGGPS, really is taking a look at our global forecast suite and trying to get a forward-looking model. And so they have some software development money as well, so we want to work with them to make sure we're on the same page as far as fine-grain development there, and as far as looking at a model, making sure that there isn't something in the model that would prevent really optimal performance on a fine-grained system. And John Bekalakis, many of you may know, is leading that effort, and he's certainly keeping an eye on that thing, as well as other parts. That of course it has to be meteorologically accurate and all that stuff too. So it's a balancing act for them. And of course, National Strategic Computing Initiative, NOAA is a deployment agency, and from our standpoint, it's something we already do, developing mission-based HPC requirements and working with vendors to let them know what our requirements are. And importantly, this is not just a hardware effort, but it's a hardware and software effort combined, and certainly my side is software part of it, and making sure our codes are viable for whatever the next generation architectures are as we go to these exascale machines that we're ready there as well. So again, this project's just starting, and really we're consolidating and accelerating existing NOAA projects. We're able to throw more staff at it. We have more reason to collaborate than we have in the past. Not that we haven't, but there's more collaboration going on. That's certainly helping us a bit. And we're able to just hit some models a little harder than we have in the past. And again, what do I say to management when or if maybe whatever your favorite fine-grained architecture isn't really the choice? What we've really seen is this effort, whether we stick with a fine-grained architecture or not, is really important for the traditional architectures. Again, beyond Broadwell, you can be high 20s, low 30s of cores. That's almost a fine grain. I mean, it's pretty much half of what a Knight's Ferry was. And so the effort is not going to go wasted. I think the codes, we see significant gains on the traditional architectures as much as we do on the, well, not quite as much, but also as we do on the fine-grained architecture. So it's good for NOAA to step back and take a look at the optimization and performance of codes and perhaps refactor them as appropriate. That's all I have to say, so thank you, and it looks like I have a little less than 5 minutes.
All right, questions for Leslie? I think we may have burned them out.
I was burned out.
Yes, before you started.
Yeah.
I'm going to ask a more sort of blue sky question. Would it be possible, is there enough commonality across your codes to somehow imagine a sort of domain-specific language that you could be expressing them in that's fairly independent of how then it maps onto particular machines? At least so that conceptually you'd capture the models, what the physics you're actually simulating is in some form that then you can instantiate that in different ways for different architectures.
Well, if I could go up into the blue sky, I would say theoretically I could imagine something like that. Again, as NOAA, we'd really like to stay out of the language development business. There are a lot of, this is a fluid flow problem. There's a lot of other atmospheric codes out there in addition to other fluid flow problems. So, hopefully either within Fortran 2.0XX or someplace that kind of domain-specific syntax will show up. I don't think we really have the kind of staffing or the kind of charter to go out and do something like that. But it'd be nice.
Anything else for Leslie? Okay, thank you.